Look at any modern airliner and you'll see them. Those upturned tips at the end of each wing. They look almost decorative. They're not. Those little vertical shapes are saving airlines billions of dollars every year. So what are they actually doing up there? To understand winglets, we first need to understand how wings work. A wing generates lift by creating a pressure difference between its two sides. As the plane moves forward, air flows faster over the curved top of the wing, which drops the pressure up there. The bottom sees higher pressure. And that difference, high pressure pushing up from below, low pressure sucking up from above, is literally what holds a 200-ton aircraft in the sky. But this elegant setup has a problem, and the problem lives right at the wingtip. You've got high-pressure air underneath and low-pressure air on top. In the middle of the wing, they can't mix. The wing is in the way. But at the tip, there's nothing stopping them. So the high-pressure air underneath curls around the edge and spills up to the low-pressure side. Now picture this happening continuously as the plane flies. That spillover stretches into a huge spiraling tornado of air, trailing off each wingtip. These are wingtip vortices, and they are expensive. All that swirling air is energy the engines paid for but didn't turn into forward motion. Engineers call it induced drag. Enter the winglet. The idea is beautifully simple. Put a vertical fence at the wingtip, and suddenly it's a lot harder for air to wrap around the edge. The vortex doesn't disappear, but it gets smaller and pushed further out behind the plane. But here's the truly clever part. Engineers shape the winglet so that the sideways airflow pushes on it at an angle. And a small component of that push actually points forward, in the direction of flight. The winglet takes some of that wasted swirling energy and converts it back into thrust. You literally recover part of the drag as free forward push. The payoff? On a long-haul flight, winglets reduce fuel burn by about 3 to 5%. That sounds small, but multiply it across a fleet of hundreds of planes flying thousands of hours a year, and you're looking at hundreds of millions of dollars in savings. The idea came from NASA researcher Richard Whitcomb in the 1970s. Today you see his invention everywhere. Classic bent-up winglets, smooth blended curves, Airbus sharklets, split scimitars, different geometries, same physics. Quick question for you. Why don't short-haul regional commuter jets always have big winglets like airliners do? The answer is B. On a short flight, the plane doesn't spend enough time cruising for the drag savings to pay off. And winglets add weight and complexity. So for puddle jumpers, the math just doesn't work out. A small vertical shape at the tip of a wing. Billions of dollars saved. One of those rare moments where engineering gets to be both beautiful and genuinely clever.